So next we will introduce the concept of characteristic function. So far, we have only considered real random variables. But using two real random variables, we can construct a complex random variable. Z equals x plus iy, where x and y are real random variables. And this would imply that the expectations, since they can be combined linearly, they can also be defined in a simple way. Now the characteristic function of the probability density function, say f of x, is defined as the expectation value of the complex quantity e to the power I tx, where t is real. Or we can write, we can express the characteristic function by this function phi of t, which is the expectation value of e to the power I tx, which, depending on whether x is discrete or continuous, can be expressed either as an integral or as a sum. So this is for the continuous case, and this is for the discrete case. It's easy to see that for continuous x, phi of t is just the Fourier transform of f of x. And the characteristic function completely determines the probability density function, because by inverting the Fourier transformation, we can re-obtain f of x. That is by the inverse transform. From the definition of the characteristic function, it is quite straightforward to see that phi of 0 equals 1, because phi of 0 is just the expectation value of exponential of 0, which is expectation value of 1, and expectation value of any constant is just that same constant. Also, the modulus of this characteristic function should be less than or equal to 1. Now, the cumulative distribution function, or the probability for any interval say from x minimum to some x, can also be found from phi of t. So if we denote it by capital Fx, and the integral is from x minimum to x on small fx, now we can use the inverse Fourier transform and substitute for f of x. We do this integral from minus infinity to plus infinity. Phi of t times e to the power minus xt. And the first integration is over dt, the second integration is over dx. If we invert the order of the integration, Then integrating first with respect to the x, allows us to write the next step. So basically we have a function of t as the integrand. We'll take the factor of iota outside. And we can finally write so this is how a characteristic function can be related to the probability for a given interval. Now in the discrete case, f of x k is given by the difference in the probability of adjacent values of x. So this is a relation that we've seen earlier. And then we can use expressions for capital F in terms of the integration over t. The characteristic function is of particular use in calculating moments. So if we differentiate phi of t with respect to t and evaluate the result at t equals to 0, so if we look at some higher derivative, and so if we're looking at the nth derivative of phi with respect to t at t equals to 0, what we get is basically n powers of iota times x. The argument of the exponential becomes 0 at t equals to 0. Everything else stays the same. So what we get is basically iota to the power n times the expectation of x to the power n. Also, the characteristic function can be written in terms of the moments by means of a Taylor expansion. So phi of t, which is the expectation of e to the power itx, and if we Taylor expand the exponential, this allows us to write sum over r from 0 to infinity iota tx to the power r by r factorial, and this can ultimately be rewritten like this as a series in t. Weighted by the moments of x. Another application of the characteristic function is to find the probability density function of sums of independent random variables. So if x and y are random variables, then their sum is also a random variable. The characteristic function of W is clearly expressible as e to the power it x plus y, which can also be written as e to the power it x times e to the power it y. Now, if x and y are independent, then expectation value of the product of some function of x and some function of y is equal to the product of the expectation values of the respective functions. So we can write the characteristic function of W like this. Or in other words, the characteristic function of the sum of independent random variables is just the product of their individual characteristic functions. Next, let's stay into the two-dimensional case. Let's study the transformation of variables. So let's look at the case of continuous PDFs first. So given random variables x1 and x2, from the joint PDF f of x1 x2 defined on some set A, if we transform x1 x2 to y1 y2, then under this transformation, the set A maps onto the set B. Now if we consider a subset of A, which under the transformation maps onto a subset of B, or in other words, if x1 comma x2 belongs to small a, which then maps to the point y1 comma y2, which belongs to the subset B, such that the probabilities A and PB are equal, then the probability that y1 y2 belong to B equals the probability that x1 x2 belongs to A, and both are equal to the integral of the joint PDF on set A. Now let's say the transformation is given like this. So y1 is one function of x1, x2, y2 is another function of x1, x2. If the transformation is 1 to 1, then a unique inverse exists. And we can express x1 and x2 as functions of y1 and y2. We also assume that all derivatives of w1 and w2 exist. Then the equality of the probabilities in the two subsets can be expressed through the equality of these integrals. So the integral over the subset A of the joint PDF can be re-expressed as the integral of the joint PDF with respect to y1 and y2 weighted by the Jacobian of the transformation. So writing explicitly, Jacobian is this transformation matrix. Therefore, the probability distribution function in y1, y2 is the probability distribution function in x1, x2 times the Jacobian. For discrete PDFs, on the other hand, the same is quite easier. So we can take the subsets A and B to contain just one point. So in that case, PB is the probability y1 equals small y1 and y2 equals small y2, and we want this to be equal to PA, which is the probability that capital X1 equals small x1, capital X2 equals small x2. These in turn are functions of y1 and y2. So the probability density functions can straightforwardly be compared as g y1 y2 equals f of w1 y1 y2 w2 y1 y2, and you can note that there is no Jacobian in the discrete case. Now next we will consider multidimensional probability density functions, and we will introduce the matrix notation for the same. So an n-dimensional random variable is a collection of n random variables, and it can be represented using a column vector. So this n-dimensional random variable x with an arrow on top the collection of x1, x2 to xn. And similarly, its transpose can be represented by a row vector. With a random variable, x is distributed according to the probability density function f of x, then the cumulative density function CDF is given by integration from minus infinity to x1 minus infinity to x2 minus infinity to x3 so on up to minus infinity to xn. The integration is over each component of the vector. So dx with an arrow on its top basically refers to dx1 times dx2 to dxn. And the PDF and the CDF are again related means of derivatives or antiderivatives. So we can write the probability density function as nth derivative, where a derivative is taken with respect to each of the components of the vector. And this derivative acts on the cumulative density function. The moments about the origin of order, say L1, L2, Ln. So L1, L2, Ln is nothing but the expectation of x1 to the power L1, x2 to the power L2, and xn to the power Ln, which is again given by an integration over n such variables of x1 to the power L1, x2 to the power L2, xn to the power Ln multiplied by the probability density function of this collection. Now, from this, if we want to compute the mean of a particular random variable, let's say we want to compute the mean of x2. And first we identify mu of 2 as mu 0, 1, 0, 0. So we've used 0 for all the other random variables and 1 for the particular random variable that we are interested in. And this basically refers to the powers L1, L2 and so on. So these means can also be written as a vector. This is the mean of the vector x. So mu, which consists of mu1, mu2 up to mu n. Where these mu1, mu2, mu n are the individual means of x1, x2, xn and so on. And if you want to compute the moments about the mean, and find as lambda L1, L2, Ln is the expectation of x1 minus mu1 to the power L1, x2 minus mu2 to the power L2, xn minus mu n to the power Ln. Now from these moments about the mean, or the central moments, we can compute quantities such as the variances. So for example, if we are interested in the variance of the random variable x1, so sigma 1 square or sigma square with respect to x1, then from the above formula it can be identified as lambda 2 0 0 0. This is just the expectation value of x1 minus mu1 square, whereas for all the other variables the power is 0. This idea can be extended to covariances as well. You can calculate sigma ij is the covariance of xi and xj, which is again expectation value or xi minus mu I times xj minus mu j. Now this is for I not equal to j. As an example, the covariance of x1 x2 is given by lambda 1 1 0 0 0 and so on. The variances and the covariances can be written in matrix form, called the covariance or the variance matrix. So we have this matrix V, which is given by E of x minus mu minus x minus mu transpose. So notice this is an outer product of the vectors, and the elements basically become sigma 1 1, sigma 1 2, all the way up to sigma 1 n in the first row. Similarly, we have sigma 2 1. This column goes all the way down to sigma n 1. So in this way the entire matrix can be populated. Now the diagonal entries are nothing but the variances of the individual random variables. Off diagonal entries can be expressed in terms of the product of the correlation coefficient and the variances of, or the standard deviations of the random variables involved in that. So the covariance matrix is clearly symmetric. We see the terms such as sigma ij equals sigma ji, and it is always possible to find a unitary transformation of the random variables x to y such that the covariance matrix is diagonal, and which would mean that yi are uncorrelated. So this is similar to the idea that we mentioned earlier, that even if two variables are found to be correlated through transformation of variables, that correlation can be made to vanish.